So as usual, just take a moment to focus and center yourself. And when you're ready, move on to the next slide. So we've already talked quite a lot about what sets are and how to describe them. And now we need to do a little more work around that. And in particular, we need to talk about the size of sets and also how we can compare two sets. So the first idea is the idea of cardinality. And we start by thinking about whether a set is finite or not, or infinite. And the way we're going to define this might seem a little bit strange, but we're going to say that a set is finite if the number of elements it has is equal to some non-negative integer. And then we're just going to say, well, any set that isn't finite must be infinite. If you were to carry on doing set theory beyond what we cover in this course, then you'd learn that there are actually different kinds of infinities, and if we're lucky we might get a little chance of that to look at that, but for the moment we're just going to say if a set isn't finite, then it's infinite. So notice that we've said that we've got a finite set has a size which is a non-negative integer, so this means it can have zero size, and you should take a moment to think about which set we've already met who has a size of 0. And then we can talk about cardinality. So if we have a finite set, then we call the number of elements in that set its cardinality. And in notation, we use two straight lines on either side of the name of the set to denote the cardinality. So let's look at some examples. So we have a set P, which just consists of 1, 5, and minus 4. That has 3 elements. So the cardinality, written with the two straight lines on either side of P, is 3. Let's look at a slightly more complex example. So we're looking at the set of all x, where x is an integer and x squared minus 49 is equal to 0. So we want to find all the integers which make this equation true. Well, if we factorize this equation, we can factorize it into x minus 7, x plus 7 equals 0, and so we see that the numbers which make this equation true are minus 7 and 7, and those are both integers, so we have that in fact our set S consists of minus 7 and 7, and therefore the size of our set S is 2. Unsurprisingly, most of the number systems that we work with, so our natural numbers, our integers, rational numbers, real numbers, and the complex numbers, are all infinite sets. And as I said, you could go and do a little bit more reading about different kinds of infinities, but for our purposes we just say they're all infinite. So now we want to talk a little bit about how we compare sets. If we have two sets, do they have the same elements? Do they have some in common? Things like that. So we begin by just looking at subsets, and we define a subset as saying that an A is a subset of B if and only if every element of A is an element of B. So it's worth taking a moment to just think about what this if and only if means. It's kind of a shorthand that mathematicians use, and really what they're saying is there are two statements that have to be true for A to be a subset. So our if and only if really says that A is a subset of B if every element of A is also an element of B, and going in the other direction, if every element of A, so now I'm looking at this part over here, if every element of A is an element of B, then A is a subset of B. So because we use things like this pretty often, we say if and only if instead of writing out both these statements, but it means the same thing. So if we have the case that A is a subset of B, then the notation that we use is this C with a little line underneath it, and that says that A is a subset of B. So if we have examples, we've got A, which is set 358, and B is the set 58326, and we'd like to show that A is contained in B. So our definition says that A is a subset of B, or A is contained in B, if and only if every element of A is also an element of B. So we go through and we check. Well, the first element that we're looking at in A is, so 3 is an element of A, and if we have a check, let's look at B. Yes, we've got a 3, so 3 is an element of B. We have 5 is an element of A, and let's just go and check. We're looking at B, and there's a 5. 5 is an element of B. And finally, the third and last element of A is 8. And if we go and do a quick check, there's an 8 sitting in B. So we see that every element of A is an element of B, and therefore A is a subset of B. You can think about how you might go about proving something like the next statement. We have that the natural numbers is a subset of the integers, which is in turn a subset of the rationals, which in turn is a subset of the reals, which in turn is a subset of the complex numbers. Let's look at one final example, and that's going to take us on to the next concept we want to look at. Suppose we have the set 1, 2, 3 and the set 3, 2, 1. A quick glance at this will tell you that these are actually the same set. And what we're going to do is we're going to show that our set S is a subset of T, and also that T is a subset of S. And you could work through this yourself. You would notice that 1 is an element of S, and check that 1 was also an element of T. Check that 2 is an element of T, and also that 3 is an element of T, and that would give you that S is a subset of T, and then you could do the same thing and get T as a subset of S. So keep this example in mind, because it's going to come up again very shortly. Before we go there, however, just a little bit more terminology. We've used the notation kind of a big C with a line underneath to say that a set is a subset of another set. Now the first thing to notice is that any set is a subset of itself. And so we're going to use a little bit of additional terminology. When we're talking about the set being a subset of itself, we call it an improper subset of itself. Anything else is called a proper subset. And if we want to make sure that we're talking about proper subsets, so we're excluding the possibility of the subset being the set itself, then we use the notation C with a line underneath and a line through that line. And the way that we can tell that B is a proper subset of A is that there must be at least one element of A that is not in B. So we have this idea of that somehow A is a little bit bigger than B, although it's not clear necessarily what we mean by bigger. So to come back to our example that we saw with our two sets that were contained in each other, we actually use that definition of subset to define what it means to be equal. So suppose we have two sets A and B. We say that A is equal to B, and we use the usual equals notation. And here again, it's if and only if every element is an element of B, and conversely, every element of B is an element of A. So really, the way we define equality is to say A is equal to B if it is the case that A is contained in B, and also B is contained in A. So we already saw that for our example of our sets S equal to 1, 2, 3 and T equal to 3, 2, 1. We saw that S was contained in T and T was contained in S. So we have S is equal to T. Just to go back to thinking about different sets, notice that here we have two sets that maybe look a little similar. We've got the set E, which is 1, 2, 3, and the set F, which is equal to the set containing 1, the set containing 2, and the set containing 3. And it's important to note that these two are not the same. For example, 1 is not an element of F, but it is an element of E. So don't get caught. We also want to introduce a little bit of notation for the set that doesn't have any elements, which we call the empty set. And the notation that we use is a 0 with a line through it, and sometimes we'll also just write a pair of curly brackets with nothing in between. And if you think about what the size of this set must be, well, there are no elements, so the size of the empty set, the cardinality of the empty set, is 0. So here are a few things for you to think about. Given any set A, we have that the empty set is contained in A. So take a moment and think about why that would be true. And as a hint, go back and look at the definition of what it means to be contained in another set, or to be a subset. And the other thing is, and this is just really a definition, we say that the empty set is an improper subset of itself. And that comes from the idea that we had, which was that in order to be a proper subset, there must be at least one element of A that is not in B. So the empty set couldn't be a proper subset of itself because it doesn't have any elements that could do that. So it must be an improper subset. So now it's a good time for you to work through some slightly more complex examples and make sure that you understand what they are going on about. So maybe head over to the textbook and have a look at these two examples. And if you have any questions, drop me an email. So one more little thing that we want to do, we've talked about counting the elements in a set, and now we want to think about how many different subsets we might have in a given finite set. And there are different ways to think about how to calculate this, but the way that we're going to look at is going to lead us into some of the work that we want to do in combinatorics a little bit later. So let's start with a question that is specific in that we want to know how many subsets the set 1, 2, 3 has. So one way to do this is to think about each subset and associate a little list with that subset, where the first element of the list is yes if 1 is in the subset, and no if not. The second element is yes if 2 is in the subset, no if not, and so on. So for example, if we consider the empty set, then its list would be no because 1 isn't in it, no because 2 isn't in it, and no because 3 isn't in it. On the other hand, if we consider the subset 1, 3, then its associated list would be yes because 1 is in it, no because 2 isn't, and yes because 3 is. So what we're doing when we do this is we're associating to each subset a unique list. And so it must be that the number of subsets that we have is the same as the number of different length 3 yes-no lists. So we could either count the number of subsets, or we could count the number of yes-no lists of length 3. And it turns out that counting the lists of length 3 that are yes-no is a little bit easier than just thinking about the number of subsets. Because what we think about is, well, if we're thinking about some 3-element yes-no list, there are two possibilities for the first element. It's either yes or no. And then there are two possibilities for the second element. Again, yes, no, and the same two possibilities for the third. And so in total, we must have that there are 2 times 2 times 2, or 8 possibilities for the length 3 yes-no lists. And so, since we know that the number of subsets is the same as the number of length 3 yes-no lists, we have that the number of subsets of our set 1, 2, 3 must be 8. If this is feeling a little weird for you, that's totally fine. We're going to do quite a lot more on this kind of counting in the next chapter when we talk about the rule of products. So this was just a little foretaste of what we do. And in fact, we can generalize this reasoning to give the following theorem, which says that if we have a finite set A, then the number of subsets of A is 2 raised to the power of the cardinality of A. So if you think about where that's coming from, in our example where we had our set 1, 2, 3, that has cardinality 3, and we had 2 to the 3 subsets. And then finally, we can take this idea of looking at all the subsets, and we can create a new set, which we call the power set, which consists of all the sets, is the set of all subsets of A. So the power set is a set of sets, and the elements are all the subsets of A. And we denote that with a calligraphic P of A. Given the previous theorem, which told us how many subsets there are for a finite set, we can work out the cardinality of the power set. It must be 2 to the cardinality of A. So let's work out what a few power sets are. Well, the set of all subsets of the empty set is just the empty set. Now, one of the things we're going to say is that the empty set is always a subset of any set. We've already mentioned that, and you've thought about why. So if we look at the power set of, for example, a set that just contains 1, it must be the empty set and also just the set itself. If we look at a set with 2 elements and we want to figure out the power set of that, well, we know that the power set is going to have the empty set as an element. And then we see, well, we're thinking all the possible subsets. Let's look, we've got 2 singleton subsets. So a singleton is a set that has just one element. And then we have the set itself. And let's just check that we've got this right. We know that the size of our set with 2 elements is 2, and we know from our little bit of work above that the size of the power set is 2, must be 2 to the 2, which is 4. And we got 4 subsets, so it looks like that's working well. So that's it as far as describing sets goes. The next section we'll talk a little bit more about how to work with sets.